As promised, in this last video, we are going to be exploring our last application of integral calculus to polar equations and their graphs, and that is arc length. Now, we've seen arc length before, and so we're going to basically derive the formula for arc length in polar from what we already know about parametric. So, if we remember that the formula in parametric has that square root, and it's dx dt squared plus dy dt squared. Now, remember in parametric, we are used to dealing with t, but every once in a while it was theta. And since we're dealing with polar and the parametricizing of polar equations into parametric, and we're always using theta, let's go ahead and think of it like this. Okay, let's think of it as dx d theta squared and dy d theta squared. Now, what we want to do is, in order to change this formula, is we're going to basically take our polar equation, and we're going to turn them into parametrics. And we've done that before, right? We did that in order to find the derivative dy dx in terms of theta. It's going to be helpful here in terms of helping us derive our thing for arc length, okay? For obvious reasons, because it involves dx d theta and dy d theta as well. Now, if we use the product rule to find dx d theta and dy d theta, we get this. Take a second, take a look at it. Okay. Now, let's go ahead and, without the radical, let's actually try and change the form of the radicand. Okay. So let's actually start with dx d theta squared and dy d theta squared. Now, if I start there and I go ahead and plug in those derivatives that I just figured out by using the product rule on x is equal to r cosine theta and y is equal to r sine theta, and I'm just going to plug those in, just substitute those in for dx d theta and dy d theta, and then I'm going to square them. Now, those are binomials, as nasty as they are, so they behave like all binomials do when you square them, right? First term squared, first term and last term multiplied together and multiplied by 2, because there will be 2 of them if you FOIL them. And then, of course, the last term squared. And the same thing happens on the second one, right here. These last 3 terms are, of course, this binomial squared. Now, one thing that you may notice is, oh my gosh, here's an r squared sine squared theta, and here's an r squared cosine squared theta. I bet if I put those next to each other, that would be of benefit. Oh my gosh, here is the derivative, here's dr d theta squared and cosine squared theta, and here's dr d theta squared and sine squared theta. Oh my gosh, if I put those close together, maybe it will be of benefit. What you also might notice is that this term and this term are negatives of each other. They are additive inverses, and therefore they cancel each other out. So let's take what's left and reorder it. Okay, I basically took this r cosine squared theta and put it next to the r squared sine squared theta, and those are my first 2 terms, and then these 2 came here. Now, I swapped the order because we're used to seeing the Pythagorean identity as sine squared plus cosine squared. But addition is commutative, it's just as true the other way. I was just doing it for sort of aesthetic reasons. Now, we basically factor by grouping, okay? Group these 2, group these 2, factor out the r squared, that goes to 1. Factor out the dr d theta squared, that goes to 1. And what I'm left with is r squared plus dr d theta squared. And all of this has been legal, so this is equivalent to that if we're dealing with a polar equation. Now, here's the thing. Someone raised in class the question of, well, isn't that just a formulaic version? Couldn't we do it just by using the particular x is equal to r cosine theta and y is equal to r sine theta? Use the particular parametric equations that I can glean from the polar. And the answer is yes. But like all formulas, they're basically useful to the extent that they are A, easy to memorize, and B, save you time and effort. And I think that this actually qualifies on both accounts, which is why I went ahead and showed it to you, while other formulas I'll show to you and discourage you from using, right? So anytime I actually encourage you to use a formula, it's because I believe that it's easy enough to memorize and it's going to benefit you, okay? Now that we have basically changed the form of the radicand, let's go ahead and plop it into our, underneath the radical and into our integrand, and this becomes the polar form of the arc length this becomes arc length formula for polar equations. And so let's go ahead and let's do an example. What we're going to do is we're going to go back to that first example where we were looking for the area of that petal in the first quadrant. Now we're going to take that same equation and we're going to find the arc length for that petal. And of course, to use our formula, we're going to not only need r, but we're going to need dr d theta. Now, if we have r and we have dr d theta, and we know the limits of integration, which we do, it's 0 to pi over 2, still, same as it was when we did the area, then our formula of L is the length equal to the integral from alpha to beta of that radical, r squared becomes that r squared. Dr d theta squared becomes that dr d theta squared. Now, I haven't tried to work this out by hand. It probably is doable, but in the interest of saving, space on the paper and time during this video, I went ahead and plopped it into my calculator and basically evaluated it that way and got this approximation, 9.688. Okay, so let's go ahead and let's actually do an example together. Now, we find the arc length of the given curve over the given interval. Now, you should recognize this as a cardioid, okay? This is a limison where the constant and the coefficient are the same. That means that there will not be an internal loop because it can never be negative, but it will come and touch the pole because it can be 0. All right. Now, what I need here, let me a second, okay. I'm going to go and plop that in. The window is, sure, the window's just fine. Okay, and there is our cardioid. Not that we really have to know what it looks like, but it's always nice to know. I'm always a big fan of the visual perspective. So, we have r. What we lack for our formula is dr d theta. 2 obviously goes to 0, and cosine becomes negative sign, so it becomes negative 2 sine theta. Now, I sometimes like to simplify the radicand before dumping it underneath the radical and into the integrand. And in this case, it winds up being 2 plus 2 cosine theta squared plus negative 2 sine theta squared. And if you multiply it out, right, you're going to get, basically, when you FOIL this, you can factor out the 4 if you want, right, because there's a common factor of 2, but that 2 is also squared. It doesn't really matter. You wind up getting basically 4, right, 2 times 2, plus 4 cosine theta, actually plus 8 cosine theta, plus 4 cosine squared theta, plus 4 sine squared theta. And of course, that right there is 4 times 1. So our radicand actually simplifies to something rather, no, actually it's not 5, that's supposed to be 8. It's supposed to be 8, right? Because this winds up being 4. So 4 plus 4 plus 8 cosine theta. Okay, so if we plug that in to our formula, and like I said, you probably could, I mean, you can at least factor the square root of 8 out and have, 2 root 2 right here, and then under the radicand, you're going to have 1 plus cosine theta. And of course, that's probably possible to do by hand, but let's go ahead and just plug it into our calculator. Okay. Now, you could remember that you can actually do the derivative in here. So let's go ahead and do that. Let's go ahead and do alpha window, right? Because it winds up being F2, and so we get the derivative formula. And usually, like I said, this oftentimes is used on the home screen to evaluate the derivative at a particular value. And you would put theta is equal to like pi over 2. But if you just put theta is equal to theta, then basically R2 will automatically become -2 sine theta, or basically the derivative of whatever you put into R1. So we go back to the home screen, and remember that this is basically going to be 0 to 2 pi. 2 pi, not 25, say one thing and my hand does another, of R1 squared plus R2 squared d theta. So let's see what that looks like. 0 to 2 pi square root of R1 squared plus R2 squared, and then d theta. And that's 15.9999999. Okay. Well, remember that this runs it through an algorithm in the calculator, and that actually accounts for the fact that it is not a pure 16, which actually it winds up being. So if you want to do it this way, okay, and basically I want to confirm the fact that those are the same value, 1 plus cosine theta d theta, and voila. Okay, and because of the imperfection of the algorithm, that's close enough to confirm the fact that this arc length is 16. Now, what we're going to do is satisfy the curiosity of the person who asked if we could do that by procedure rather than by formula, basically by doing it with the old formula for but basically the parametric formula for arc length. Okay, well, let's go ahead and do that. So remember that it was R 2 plus 2 cosine theta. So that is our equation. If we want to turn it into parametric, we basically take R cosine theta and R sine theta. Now, for a little ways, we're going to be running on two sides of the paper. So let's sort of draw a dividing line to keep our work kind of nice and tidy. Now, dx d theta, of course, is going to be the product rule. So you have the first times the derivative of the second plus the second times the derivative of the first. And if you clean it up and use trig, basically what happens is it winds up being -2 sine theta plus sine 2 theta. Okay? Because when you distribute this sign across here, you're going to get -2 sine theta cosine theta, and over here you're going to get -2 sine theta cosine theta, and of course that's going to be 4 sine theta cosine theta, or 2 sine 2 theta. Something similar is going to happen over here, and you need to take the derivative again by the product rule. So the first, 2 plus 2 cosine theta times the second cosine theta plus derivative of the first times the second. All right, and this, when you distribute it, you're going to get 2 cosine theta and 2 cosine squared. This is going to be -2 sine squared. You're going to get the double angle for cosine, and what you're going to get is 2 cosine theta plus cosine of 2 theta. Now, that's already a whole lot of work, but let's go ahead and do the dx. Let's go ahead and do the Radicand. while it's still not. Let's basically simplify the radicand before we put it underneath the radical and into the integrand. Whew. Okay, now are you ready for this? Because when I square this, I'm going to get 4, and I'm going to get sine squared theta plus 2 sine theta sine 2 theta plus sine squared 2 theta. And then I'm going to get, when I square this one, cosine squared theta plus 2 cosine theta cosine 2 theta plus cosine squared 2 theta. Now, you're probably recognizing the fact that a whole lot of this is going to combine and by Pythagorean cancel out. When you distribute the 4, you're going to get 4 sine squared. When you distribute the 4, you're going to get 4 cosine squared. Those obviously will go together, okay? When you distribute, you're going to get 4 sine squared 2 theta and 4 sine squared cosine 2 theta. Those are going to combine. And so what you're going to get when you get all the way down to it is you're going to get, that's 1, so you have 2, okay? And so you have 2 plus 2 sine theta sine 2 theta, and that's 2 cosine theta cosine 2 theta. Now you can factor out another 2, but notice again something that you have here, okay? I'm going to use a different color. This and this kind of look like the difference identity for cosine. So let's go ahead and factor out that extra 2, and I get 1 plus, and this is going to be cosine of 2 theta minus theta, or just cosine of theta. Now, of course, I've cut out a lot of these steps, and if you did all the steps, you'd be pouring off the bottom of the page probably. But once you get to here, you can then put it as, 2 root 2 from 0 to 2 pi 1 plus cosine theta d theta. But notice this doesn't look like much more work, but I've skipped a whole lot more steps in doing it this way. And I do still, however, get to that same integral that I had in the last time. So it's still going to be 16. So the answer to the question is yes, you can do it by parametric. But like I said before, I share formulas with you and encourage you to use them when they are expedient and when they're easy to memorize. And this one actually is a yes on both accounts. All right. Let's go ahead and take a look at this one. Now, we usually don't look at spirals, but in terms of arc length, it's a fun one. So let's go ahead and let's find the arc length of r is equal to theta from 0 to 2 pi. Okay, well, let's find our dr d theta. Well, that's easy. That's just 1. So that means that my r squared plus dr d theta squared is going to be theta squared plus 1. So 0 to 2 pi, theta squared plus 1 d theta. And I could plop it into my calculator, or I could do it by trig sub, right? And if I did it by trig sub, I would say theta is equal to tangent of, and we'll call it alpha. And basically d theta winds up being secant squared alpha d alpha. And when you actually transform that, it becomes, the square root of tangent squared alpha plus 1 and secant squared alpha d alpha, which, by the way, is going to wind up being that lovely one that we remember, secant cubed. And who wants to do that all over again? Do you remember it? Okay, because I barely do. But let's go ahead and let's just, on this one, for the sake of time, just plug it into our calculator. And when we do, we get 21.256. Now, that brings us to the end of our discussion of the application of integral calculus to polar equations. As always, please do shoot me an email if you have any questions. Bye.